Good morning, everyone. Thank you for joining us today. In our last discussion, we really dug into the fundamental building blocks of the nano world. Today, we're exploring the application that has, without a doubt, shaped our modern era. How nanotechnology became the quiet, invisible engine powering every single piece of electronics and computing we use. So let's start right there. Just how essential is nanotechnology to the devices we use every single day? Our phones, our laptops. I think for a lot of people, it's still an abstract term, and they might not realize just how deeply it's already woven into our lives.
That's really the perfect place to begin, because essential or integral almost doesn't do it justice. You see, nanotechnology isn't just a component of modern electronics. For all practical purposes, it is modern electronics. If you're using a smartphone or any computer made in the last decade, you're holding the culmination of decades of hard-won battles in nanoscale engineering. Every single major leap in computing power, every incredible new device that's come out, is a direct consequence of our growing mastery over matter at this tiny scale. It is, and I don't think this is an exaggeration, the single most commercially successful and society-altering application of nanotechnology so far.
Okay, so it's not just a component, it's the whole engine. And the performance of that engine has been famously charted by Moore's law. Could you break that down for us and explain how nanotechnology became the absolute critical fuel that kept that law alive for so long? Absolutely. Moore's law started as a simple, powerful observation. The number of transistors you can fit on a chip roughly doubles every 2 years. That doubling is what gave us the exponential growth in computing power we've all experienced. But to keep doubling the number of transistors, the transistors themselves have to get smaller and smaller. And for about 2 decades now, that shrinking process has been happening entirely in the nanoscale. Now, that number you see on the slide, 2 nm, that's key. By 2025, the industry is manufacturing at what's called the 2 nanometer node. It's important to understand this is more of a marketing term today. It's not a literal measurement of one part. But the truly critical features on these chips, the tiny gates that control the electrons, are indeed getting down to a mind-boggling 10 to 15 nanometers wide. To even do this, we had to invent completely new technologies, like extreme ultraviolet lithography, or EUV. This uses light with such a short wavelength that it's absorbed by almost everything, even air, so the entire process has to happen inside a massive vacuum. At this scale, you're not just carving silicon anymore. You are quite literally arranging handfuls of atoms to build a working switch. It's one of the most astonishingly complex manufacturing processes humanity has ever created. Arranging handfuls of atoms? That sounds incredibly fragile. As we push transistors down to this fundamental limit, what are the major walls we're crashing into? I've got to assume the classical physics we all know and love starts to get really weird and very unhelpful.
You're spot on. We've run smack into what engineers call the nanoscale power wall, and it's a brutal problem with a few key parts. First, as the slide shows, is quantum tunneling. Okay, so in a transistor, you need an insulating barrier to stop electrons when the switch is off. At the nanoscale, that barrier might only be 5 or 6 atoms thick. An electron starts behaving less like a tiny ball and more like a wave of probability. And there's a real chance it can just disappear from one side and reappear on the other, tunneling right through that off switch. This creates leakage current, which wastes a ton of power and generates useless heat. Second, there's heat dissipation. When you pack trillions of these leaky atom-sized switches into an area the size of your thumbnail, the heat density can actually exceed the core of a nuclear reactor. You literally can't get the heat out fast enough, which puts a hard cap on the chip's speed. And finally, there's the sheer manufacturing complexity. We are trying to build trillions of components with almost atomic perfection with nearly zero defects across an entire silicon wafer. The fabrication plants, or fabs, that do this cost over $20 billion and are some of the cleanest places on Earth because one tiny speck of dust can ruin a processor worth thousands.
Wow. So with these fundamental physics and engineering roadblocks, it sounds like the old strategy of just making things smaller, what's called the more is more approach, is pretty much at the end of its line. How is nanotechnology creating a new way forward with this more than more idea? Exactly. And that's really the core idea behind more than more. The industry figured if we can't just keep shrinking, we have to get much smarter. So instead of just making transistors smaller, we're using nanotechnology to completely redesign their physical shape. A huge breakthrough here is the gate-all-around field effect transistor, or GAFET. Think about it this way. A traditional transistor is like trying to stop water in a hose by just stepping on it. It's not very effective. Water still squirts out the sides. That's your leakage current. A GAFET, on the other hand, is like wrapping your entire hand around that hose and squeezing from every direction. By wrapping the gate, or the switch, completely around the channel where the electrons flow, you get almost perfect control. This new 3D design basically chokes off those quantum leaks we were just talking about. It leads to transistors that are not only faster, but way more power efficient, even at these tiny scales. It's a fundamental shift from brute force shrinking to intelligent 3D design. That's a fascinating evolution for classical computers. But now I want to pivot to a totally different way of thinking, a new paradigm that's built from the ground up on these very same nanoscale principles: quantum computing. How is this revolutionary field at its heart a nanotechnology? It's the perfect pivot, because quantum computing is really where nanotechnology meets the deepest and strangest parts of physics. You know, a classical computer thinks in bits, clear zeros or ones. A quantum computer works by directly controlling individual quantum systems: a single trapped atom, a single photon of light, or a tiny superconducting circuit that behaves like one quantum object. And the basic unit here is the qubit. And this is the key point. These qubits are not just ideas on a whiteboard. They are, for all intents and purposes, artificial atoms, incredibly delicate nanoscale devices that are patterned with nanometer precision in the same multi-billion-dollar fabs we use for our best classical chips. We're using the most advanced tools of nanotechnology to build, isolate, and control the very units of quantum mechanics itself. So we are literally building artificial atoms. Can you walk us through the principles that make these qubits so much more powerful? What do terms like superposition and entanglement really mean in practice?
Absolutely. As the slide shows, the difference is just profound. A qubit takes advantage of a core quantum idea called superposition. The best analogy I know is a spinning coin. While it's up in the air, spinning, it isn't heads or tails. It's in this fuzzy, probabilistic state of being both at once. Only when you measure it, when the coin finally lands, does it collapse into a definite state, either heads or tails, a 0 or a 1. So a single qubit can explore more possibilities than a simple bit. Then you add entanglement, which is what Einstein famously called spooky action at a distance. You can link two cubes so their quantum fates are tied together. If you measure one and it collapses to a 0, you instantly know the other one is a 1, no matter how far apart they are. When you combine these two ideas, a quantum computer creates a problem-solving space that grows exponentially with every qubit you add. That's what gives it the potential to solve certain kinds of problems, like designing new medicines or breaking today's encryption, that would take even the biggest classical supercomputer billions of years to crack.
It's an amazing concept, but it also sounds unbelievably delicate. It seems like whether we're talking classical or quantum, we keep coming back to the physical limits of our materials. For decades, silicon has been the undisputed king. Why is its reign finally being challenged? You've put your finger on the central issue. As incredible as silicon has been, we are basically squeezing the very last bit of performance out of it. Those problems with quantum tunneling and heat are fundamental to silicon's atomic structure at these scales. And that's exactly why the hunt for a post-silicon material is one of the hottest areas in nanotechnology research. One of the top contenders is the carbon nanotube, or CNT. The idea here is to build a carbon nanotube field effect transistor, a CNFFT, where you replace the silicon channel with one of these incredible molecules. As you can see in the table, the huge advantage is something called electron mobility. In a CNT, electrons can move with ballistic transport, which means they flow almost without any resistance, kind of like a bullet fired in a vacuum. This is totally different from silicon, where electrons are constantly bouncing off atoms in the crystal, which generates heat. This special property means that CNFTs could, in theory, be up to 10 times faster and use 10 times less power than the best silicon transistors. That would be a revolution, letting us smash right through that power wall we talked about. 10 times faster and 10 times more efficient? That would be a complete game changer. But I'm guessing if it were that easy, our phones would already be running on carbon. What are the massive hurdles that are keeping CNFETs from mass production?
Right. That's the multi-billion-dollar question. The potential is incredible, but the manufacturing challenges are just as big. First is precise placement. A modern chip needs billions of transistors. So you have to somehow grow or place billions of identical carbon nanotubes in perfect alignment across an entire wafer. Researchers are trying all sorts of things, like using chemical templates to guide the nanotubes to assemble themselves in the right spots. Second is purity. When you make carbon nanotubes, you get a mix. Some are semiconducting, which is what you need for a switch, but others are metallic, which act like tiny wires that are always on, short-circuiting the transistor. We need to get to 6 nines purity, 99.99999%, which is an enormous purification challenge. And finally, you have to make reliable contacts. How do you attach a metal wire to a component that is literally a single molecule wide and make a good connection? Scientists are working on different metals and chemistries to make that connection seamless. Solving these 3 problems is really the holy grail for the future of electronics.
Okay, let's shift gears a bit from just raw processing power to another huge area, sensors. We're hearing the term nanosensor more and more. What exactly is a nanosensor, and what is it about the nanoscale that gives them this almost supernatural sensitivity? The secret to their sensitivity is a simple but incredibly powerful property, a massive surface area to volume ratio. The best way to picture it is to think of a sugar cube. It has 6 sides, so that's its surface area. But if you crush that cube into a fine powder, you still have the same amount of sugar, but the total exposed surface area is now gigantic. A nanosensor is the same idea. It uses nanomaterials to present a huge sensing surface to the world, so when even a single target molecule, like a virus protein or a pollutant, lands on that surface, it causes a big, easy-to-measure change in the sensor's electrical properties. That's what lets them detect things down to parts per billion, or even in some cases, a single molecule.
So it's all about maximizing that contact surface. And speaking of miniaturization, this also applies to tiny machines, doesn't it? Can you explain what these terms on the slide, MEMS and NEMS, are?
Exactly. MEMS and NEMS stand for micro and nano electromechanical systems. These are basically microscopic and nanoscopic machines. We're talking gears, levers, vibrating beams, all built right onto a silicon chip. The accelerator in your smartphone is a perfect example of MEMS. There's a tiny, suspended weight inside, and when you tilt your phone, it moves. Tiny capacitors measure that movement and tell your phone which way it's oriented. NEMS, nano electromechanical systems, is taking that whole idea and shrinking it down to the molecular level. And at that scale, things get really amazing. You can build tiny vibrating beams that oscillate at gigahertz frequencies, which could be used to build filters for future 6G communications. And their sensitivity, as you mentioned, becomes almost absolute. A NEMS cantilever, which is like a nanoscale diving board, can be so precise it can actually detect the added weight of a single virus particle when it lands on its tip. That's what the number 1 on the slide represents, the ultimate goal of sensitivity, detecting a single unit of something, whether it's a molecule, a protein, or even a single quantum of energy. It really turns our devices into tools for fundamental science.
It's just incredible to think about these invisible machines running our world. Now, everything we've talked about so far, chips, sensors, they're all built on these hard, flat, rigid silicone wafers. But nanotechnology is literally changing the shape of electronics. How is it breaking our devices free of those rigid boxes and making them flexible, bendable, and even stretchable?
It's opening up a completely new design space. Nanotechnology really attacks this problem from a few different angles. First, you have conductive inks. These aren't like the ink in your pen. They're liquids filled with silver nanoparticles or tiny flakes of graphene. You can literally use an inkjet printer to print flexible circuits onto plastic or even fabric. Second, you need flexible transistors. So instead of a rigid silicon crystal, you can use a tangled mat of semiconductor nanowires or those carbon nanotubes we mentioned and embed them on a flexible base. And finally, for screens, you need something that's both transparent and conductive. The old material, indium tin oxide, is brittle like glass. Nanotechnology gives us incredible alternates, like a random mesh of silver nanowires. It's so sparse that it's almost completely transparent, but the wires are so conductive it works as a perfect touch sensor. Or you can use graphene, a sheet of carbon that's only 1 atom thick. It's stronger than steel, more conductive than copper, and almost perfectly clear. These materials are the magic behind a screen that can bend. So what are some of the most exciting real-world applications of this that are starting to move out of the lab and into our hands?
Well, the most obvious examples are the foldable smartphones and rollable TVs that are now actually on the market. Those exist entirely because of these new, flexible, nano-enabled conductors and displays. They would be completely impossible with older materials. But I think the more profound applications are emerging in health and wearables. We're seeing the development of what's called electronic skin. These are thin, flexible, almost tattoo-like patches that you can stick on your body. They can be loaded with nanosensors to continuously and non-invasively track things like heart rate, temperature, blood oxygen, and even glucose levels with clinical-grade accuracy. It's all about moving medical monitoring out of the hospital and making it a seamless part of daily life. And that integration is set to go even deeper, to the point where it just disappears into the things we wear every day. The next frontier here is smart textiles. We're moving beyond clipping a device onto our clothes and toward weaving the electronics and sensors directly into the fabric itself. Using those conductive inks, we can literally print circuits and sensors right onto a t-shirt. Imagine clothing that performs a constant EKG to monitor your heart, or athletic wear with nanosensors that analyze your sweat in real time to tell you about your hydration and electrolyte levels. It's all part of this vision of making technology completely ambient and personal, and it's all powered by our ability to build with nanomaterials. This has been a truly incredible tour, from the heart of a massive supercomputer all the way down to a smart t-shirt. So if you were to pull all of these different threads together, from those 2-nanometer transistors and quantum bits to flexible e-skin, how would you define the ultimate overarching role that nanotechnology has played in our digital world?
The impact is total. Nanotechnology isn't just a field that influences electronics, it is the fundamental physical engine that has driven the entire digital revolution, full stop. Its role is absolutely everywhere. As we've seen, it powered the relentless march of Moore's law that gave us the cheap, powerful computing we now take for granted. It provides the literal, physical hardware for the brand new paradigm of quantum computing. Looking ahead, nanomaterials like carbon nanotubes give us a real path to get past the limits of silicon. And things like nanosensors and flexible electronics are creating entirely new ways for technology to merge with our bodies and our world. So, just like the quote says, from the biggest AI supercomputers to the simple fitness tracker on your wrist, nanotechnology is the one single common denominator.
That's a perfect way to summarize it. It's the invisible foundation of our entire digital lives. It really makes you wonder, as we get better and better at building atom by atom, where's the final limit? Or is there one at all?
This has been an amazing look at the hardware that runs our world. Next time, we're going to shift our focus from electronics to biology, exploring the incredible and sometimes controversial field of nanotechnology in medicine and biology. We really hope you can join us for that discussion. Thank you all for lending us your time and your curiosity today. To stay up to date with all of our latest deep dives, please make sure you subscribe to our channel, Tech AI and Beyond. We'll see you next time.